First, our problem description. Search an ordered array. Yeah. Our problem number 11. Here, this information is important. Ordered array. Yeah. If it's unordered, then we can only use linear search. We learned before linear search in our module 1. Yeah, that's for unordered array. But now we organize the data. We make our data organized. Yeah. Usually this step is very expensive. That means you need to do sorting, right? How do you make ordered data? Given original data usually unordered. Yeah. If you want to make it ordered, you need to pay some quite expensive cost with that data organization, that step usually quite expensive. Yeah. After you pay that part, we can treat as investment because the rewarding is much bigger than the amount of time we pay. After that, we can take advantage of the property of our data because we have organized the data. That property we can take advantage of to make our algorithms more efficient. So this binary search, we want to take advantage of this ordered data property. Okay. All right, first let me describe the problem. Given an ordered array and a search key V. Okay, yeah. Question, how to find an index I such that V equals A of I? Yeah. Here you can see this problem description very similar to the one for our linear search problem. The only difference is we changed the unordered word to ordered array here, that word. Only one word change. So we get this problem number 11. Yeah. All right. So the main question, we need to find a solution by taking advantage of this new property. Yeah. Data, ordered data property. Yeah. All right. Let's do analysis. Yeah. Here, how to take advantage of this ordered property. Yeah. So that's the most important thing we need to do. Yeah. The idea, we use our old idea, reduce the problem size by the ordered data property. Reduce the problem size. We used this way many, many times before. Now, the question is how to reduce the problem size, right? How to reduce the problem size. Here we have the important ordered data property. So we want to use this property to reduce the problem size as much as we can. Yeah. So that's the basic idea. Or we can treat as the strategy. Yeah. So this is the strategy we want to take. Yeah. All right. By elimination method. Yeah. Elimination. Yeah. How to do elimination? Yeah. So let's look at the details. Yeah. How can we take advantage? Yeah. All right. We need to explore the order property. Yeah. Okay. Yeah. All right. So here, let's consider a typical situation. Yeah. But this array is ordered. Yeah. So that information is important. Yeah. Now, we want to find the location for this V key. Yeah. Where can we find this key in a given array? Which location? Okay, yeah. We can do comparisons here. We can do comparisons. Here, I show you one example, one special case, we do the comparison. Here, these two arrows means we compare V with last element A sub n minus 1. Our first try. When we do our first comparison, this is our first try. Okay. Then let's consider what is the possible results we may have after this comparison. Similarly, we can compare this V with any element in this array. And we need to look at after one comparison, how much progress can we make? We want to see that after one comparison, how much progress we can make. Okay, yeah. All right. Question, after one comparison, how many elements can be eliminated? So that's the elimination method we are using in this situation. Okay, yeah. All right. Let's look at the first special case when we compare V with the last element A sub n minus 1. There are two possibilities. The first one, the best case, V is greater than A sub n minus 1. Is greater than. Or we can say greater or equal, including the equal, because when V equals the last element, it's also the best case. The best case, it means after one comparison, we get the search result. That's the best case. Only one comparison, we can make our conclusion. We can make our conclusion. The conclusion is if V equals to the last element, then we find it. We can return the index I for which A of I equals V. That's the solution. Or another case, V strictly greater than the last element, then we can also make our conclusion. This array does not contain the element of V, and we can tell the location of this V is greater than the values of all the elements in the given array. So we have that conclusion. So that's the best case. One comparison, we can make that conclusion. Another case, other cases, V less than A sub n minus 1. Yes. So you can see we have two possibilities. The first possibility, the best case. The second possibility, V less than A sub n minus 1. That means we need to do more comparisons. For this situation, we need to do more comparisons. We can eliminate, in this case, we can eliminate the last element. This A sub n minus 1, we can do the elimination, but still we need to consider V in the first n minus 1 elements. We need to consider that case. First n minus 1 elements, still we need to find the location for this V. A lot of work we need to do. All right. Here, by this first try experiment, do you have any useful information you can discover by this first try. Yeah. So let's see. Yeah. Murphy's law. Here, I like to, talk about the Murphy's law. Yeah. Why first, the Murphy's law, right? Yeah. From your real life experience. People, talk about this Murphy's law. So what's that? Anything that can go wrong will go wrong. Okay? Yeah. So here, what do you mean here, Murphy's law here? Because the best case, that's something we like to have. This part, that means we need to do a lot more work, We don't want to see this case. We want to see the best case. So this case for us, it means something go wrong, right? And we want to avoid that could go wrong. But based on Murphy's law, that can go wrong, okay? That can go wrong. So that means we need to focus on this wrong case, okay? Something wrong, this wrong case we need to focus on. Best case, we don't worry about it, okay? We like to have it, yeah, we don't worry about it. But the wrong part, that's we need to really, do a lot more effort to find a solution for that wrong part, okay? Yeah. So here you can see from the problem size reduction point of view, reduce the problem size. From the problem size reduction point of view, how much size, after one comparison, how much size we do the reduction? Only one. We only eliminate one element. That reduction is too small, right? So this reduction, too small. So that's not a good reduction way, okay? Yeah. Definitely, we want to do better, faster reduction than this one, right? Yeah. So our next round experiment, we want to do better than that, okay? Yeah. So compare the element right in the middle. Yeah. All right, right in the middle. We call it a median. Yeah, so median. Yeah. Here regarding the median, yeah. So what's the definition of median? What's the definition of the median? Right? Yeah. So sometimes some students ask me this question. Yeah. We know the definition for the median. If you sort that array, the one right in the middle position, it is the median. Yeah. For all the number of elements, then you have no problem. Suppose you have all the number of elements. The one in the middle, there is no argument, right? Yeah. So there is one in the middle, absolute middle. Yeah. Nobody can argue with that. But when you have even number of elements, then which element we call it the median? Because there are two elements, they are in the same position with respect to the middle, in the sense of middle position. Right? Yeah. So usually we call the left median. Yeah. So the left one, we can call the left median. The right one we call the right median. Okay. Yeah. So you can see there are two median, but left median is the default median. Okay. Left median is the default median. Yeah. That means if we do not say left median or right median, we just say median, we refer to the left median. Okay, yeah. Because in that way, there is no confusion. Otherwise, people always ask us, what do you mean the median? Do you mean the left median or the right median? Yeah. By default, we mean the left median. Okay, so then there is no uncertainty. Okay, everything is clear. No matter we have even number of elements or all the number of elements in the given array. Okay, all right, so after we have this median concept, yeah. Then next, oh yes, strategy, yeah, balancing principle, yeah. So here next, right. So this idea, yeah, every time you can throw away 1/2 of elements, yeah. So this idea, let's talk about next, yeah, next, all right, yeah, efficiency, yeah, right. Here, let me use this diagram to show you the idea. Okay, yeah. So the best way for the elimination, when we choose an element somewhere in the middle of the array to do comparison, to do our first comparison, the middle one gives us the best possible result. Can you see that? Can you see this property? Yeah. When you choose the median, here, let's assume this is the median, okay? Yeah. When you choose the median element as for your first comparison, you can get the best possible result. Why? Why? Okay, yeah. So here the idea is pretty simple. Because after one comparison, you can drop one of the two subarrays, either the left subarray or the right subarray, right? You can drop one of the two subarrays, right? Based on your comparison result. Yeah. If the median is, yeah, let's say the median, yeah, let me use M. The median is greater than V, greater or equal to V. If your comparison tells you M greater or equal to V, that means the left subarray can be dropped, right? That means, yeah, because if it equals, yeah, let's say if it equals, you get a solution, all right? Yeah, let's consider if equals, you already have the solution. You stop after you find the solution. You should stop, right? Yeah. So we only consider M greater than V. If M greater than, you can drop the whole left half subarray containing the median. Okay, so you only need to consider the right subarray, excluding the median. All right. Similarly, if M less than V, you can drop the right half of the subarray. Yeah. So the problem size reduction, you can reduce approximately 1/2 of the problem size, right? Yeah. Approximately 1/2 of the problem size. But think about, if you do not compare with the element in the right in the middle, yeah, let's say, suppose this is your array. If you compare the element approximately 1/3 of the right, counting from the right end, 1/3, although you have a chance to drop the bigger subarray, but you have another chance to drop the smaller subarray. Think about that. You have smaller chance to drop smaller subarray. That means 1/3 original problem size. That reduction is slower than 1/2 of the problem size, right? Here we drop the 1/2 of the problem size, but here you may drop 1/3 of the problem size. That means your problem size reduction is slower than this median way. Median way is faster. Okay, yeah. So that tells us this median way is the best way. Overall best way. Okay, yeah. All right. Now, next round, yeah, because after one comparison, so think about that. After one comparison, we reduce the problem size by 1/2. Okay, let's do another comparison, our second comparison. We reduce the problem size by another 1/2, drop another 1/2 of the current array size, and so on. So we keep doing that, and after certain number of comparisons, the array size is reduced to this small. How about that? Here, I use this table to show the data size we have after each comparison. Yeah. After the first comparison, the data size becomes n/2. Second, it becomes n/4, and so on. After k comparisons, the problem size or the data size becomes n/2 to the kth power. Yeah, so that's what we can get after our elimination methods. Here we use the elimination method. That's what we can get. Yeah. But next question, we need to determine how can we stop this process. Yeah. We have to find some point that we should stop. Okay, yeah. We need to determine after a certain number of comparisons, we get to the last element. No more element for us to do further comparison. Yeah. We need to find that point. The question, how to determine that point? All right. Question, at what time should we stop splitting? Yeah. When the data, because you cannot split forever, right? So you have to stop somewhere. So we need to determine the point where we should stop splitting. All right. We need to set up some formula for us to determine that the number of k. What is that k? For the splitting, for the last splitting. Yeah, let's say in this way. Which k gives us the last splitting number? All right. Think about when the data size less than 1, do you need to do further splitting? Data size less than 1, that means the subarray, the remaining subarray can only cover one element, right? Yeah. Cannot cover 2 elements, right? If 2 elements, the data size should be greater or equal to 1, right? Yeah, greater or equal to 1. You know, the data size here, we consider the length between 2 elements. If it's 1, yeah, the difference is 1, that means you may have 2 elements. Here, yeah. Oh, I need to, yeah, let me see. Okay, good. Yeah, still there. All right. All right. Our analysis. only when the data size is strictly less than 1, we can make sure we only have one element left. If one element left, that means we do not need to do further splitting, only one element. There is no sense to do another splitting, right? Yeah. So this condition tells us that is the condition for our last comparison. Okay? Yeah. Yeah. So let us write this condition precisely in this way. Yeah. All right. So that means when after k comparisons, the size should be strictly than 1, but after we do k minus 1 comparisons, the size should be greater or equal to 1. That means you need to do one more splitting. Why? Because your data, the number of data items in your current subarray greater or equal to 2. You have at least 2 elements. You can still do one more splitting. Yeah. Now the question, how to find that k? How to find that k? By solving this inequality. Okay, so let's solve this inequality. Yeah. After simplification, yeah, we get 2 to the k minus 1 less than or equal to n less than 2 to the k. Yeah. Then we take natural, not natural log of base 2, right? Because power of 2, we should take a log base 2. Yeah. Then we get k minus 1 less than or equal to log base 2 of n less than k. Can you get the range of k? Yeah. So we can write the range of k. Yeah. Here we derive the worst case formula. The worst case. Yeah. Because the best case, one comparison, right? After one comparison, we find the solution. That's the best case. But worst case, we need to do many comparisons until there is no comparison needed. That's the worst case. Yeah. So for that k, let's find that. All right. Yeah. So this formula can be translated to this formula easily, right? Yeah. So you move, some numbers from left to right, right to left, you can get this express inequality. Yeah. Equivalent to this one. Yeah. But this time we want to describe the k, because we assume n is known, n is given, right? Yeah. And we want to find a formula for k. Okay, yeah. By using floor function and a ceiling function. Yeah. Floor function and a ceiling function. Okay, yeah. Can we write an equality way? Well, yeah, here, this inequality still, there is some uncertainty, right? If you want to find k using this inequality, there is still some uncertainty, right? Yeah. Not very good, not the best one. So we want to find an equality, because with that equality, there is no certainty, no uncertainty. Yeah. Everything is clear. Yeah. So we need to write it as an equality. So to get that, let's start from this original equality. Yeah. Before we take the log base 2, we have this inequality, right? before the log base 2. Yeah. Why we go back to the previous inequality? Because look at here, strictly less than, we want to tighten. We want to tighten this inequality, make this inequality stronger. Yeah. Tighten it. Yeah. How to tighten it? Okay. Yeah. All right. Because this part strictly less than, that means if we add 1 to n, then we can make this equal sign. How about that? Yeah, because 2 to the k, that's integer, n is another integer. 2 to the k integer is strictly greater than n. That means 2 to the k is greater or equal to n plus 1, right? At least 1 more than n. 2 to the k is at least 1 more than n. In that way, so we make this improved inequality. This is an improved inequality, n plus 1, less than or equal to 2 to the k, improved inequality. Okay, yeah. Then we take log base 2, so we have a new, so look at this improved inequality. Okay, yeah. This one, we can improve it to log base 2, parenthesis, n plus 1. Slightly better, right? Yeah, because here we can use equal sign. Here, strictly greater than sign. So you can see it is an improved version. Yeah. From this improved version, we can write equality. We can write equality. Yeah. So what's that? The conclusion. For the equality, to determine this k, we have 2 formulas. 2 equivalent formulas. 2 formulas with different forms, but they give the same number. The number should be the same. Yeah. The first formula, K max, the maximum number of comparisons you need to do. So I call it K max. K max equals the ceiling function of log base 2 of n plus 1. We use this leftmost expression, log base 2 of n plus 1, but we take the ceiling function because here less than or equal to k. When you take the ceiling function, you move it up, then you reach that k. Okay, yep, that's the k max number. But the second formula, you use the rightmost expression, but you take the floor function. Yeah. So k max equals 1 plus the floor function of log base 2 of n, and these 2 formula expressions, they are equal. Okay, they are equal. Yeah, we can prove it. Yeah. All right, we can prove it if you really want to, practice your algebra skills. You can prove it by mathematical induction. To prove it, you can use mathematical induction. Okay, yeah. Here, I do not do it. Yeah, yeah, yeah. So we have this formula. This formula is given in our textbook. Yeah, in the appendix. In the appendix of our textbook, you can find this formula. They are equal. Yeah, and this formula can be proved by mathematical induction. Okay, yeah. All right. So now the conclusion. After this step, the conclusion for best case, worst case, then average case. First, the best case is 1. That's the easiest case. Second, the worst case, we just find the formula. One of the 2 formulas you can use, one of the 2 versions. Yeah, they're equivalent. You just pick one. Yeah. So here I picked the second one. Yeah. But for the average case, that's the hardest one. How to get the average case. We need to do calculation for the average case. Yeah. That calculation, you need to do a lot of work. You need a lot of work. Okay? Yeah. All right. The question, can we simply by taking the average of the best case and the worst case in this way? Yeah. We know the best case. We know the worst case. Can we simply using the average of the best case and the worst case for the average case? Yeah. The answer is no. The answer is no. Okay? You cannot use this formula. If you use this formula, it is less than the real average. This number, you get less than the real average. Our real average is much bigger than this number. Okay? Yeah. Actually, the real average is very close to the worst case. Okay? Yeah. A little smaller than the worst case, but very close to the worst case. Now you can see the average case. Yeah. Not right in the middle. Not right in the middle of the best case and the worst case. It is very close to the worst case. That's the average. Yeah. Yeah. All right. Why is that? Yeah. 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 All right. Here, I can use a simple example when n equals 7. Yeah, I can show you, the average. Yeah, so you can get an idea. Yeah. All right. So our next topic, B.3, average case efficiency of binary search. And let me use n equals 7 to show you the answer. Yeah. So what is the answer? Okay. All right. Here, let's look at this example, n equals 7. First, n equals to 7, what is the worst case? Yeah, based on our formula, worst case. Okay, 1 plus floor function log base 2 of 7. This is the formula. 1 plus 2, right? Yeah, log base 2 of 7, 2 something, less than 3. Yeah. Log base 2 of 8, that's 3. Log base 2 of 7, less than 8, strictly less than 8. So 2 point something. Then the floor function is 2. 1 plus 2, that's 3. Okay, yeah, that's the worst case. The average case should be smaller than 3. Yeah, but how close to 3? Yeah, so let's look at how close to 3. Yeah, all right, so let me show you how to find the average. All right. Data, 7 elements sorted array. Yeah, like this. Yeah. Here I draw a diagram. Yeah. Then we run the binary search. And when we consider all the possible cases, 7 cases, then we can draw a binary tree. The binary tree to represent all 7 cases here. Okay, yeah. Yeah. All right, here we make a simple assumption. V is in the array. Yeah, V is in the array. Yeah. If V is not in the array, then we need to do another assumption, the probability. Some probability P for which V is in the array. Yeah. Here, to make the discussion as simple as possible, let's make this assumption, V is in the array. All right, yeah. So then let's consider, yeah, right, yeah. So the P, yeah, you need to use that P. Now let's consider the first comparison based on the binary system. We need to compare V with element at position 4, right? Yeah, absolute middle location. That's our first comparison. Compare it with element with position 4. Yeah, position number 4. Yeah, that's our first comparison. Okay, then we need to go to the left branch or right branch based on the comparison result, greater than or less than. Okay, all right, so we have two branches. For the left branch, we have 3 elements in the left branch, but the second comparison, we need to compare V with element at position 2. So we put this node as the root of the left branch. Similarly, element with position number 6 should be at the root of the right branch, because that's the one we need to do the second comparison. Yeah. So these two elements, we need 2 comparisons to get a match. Okay. Then going down, yeah, another left-right consideration. So 1 at the left of node 2 and 3 at the right node of 2, and so on. Okay, yeah. So this is our final binary tree representing the comparison situation for this 7-element sorted array, ordered array. Okay, yeah. And the third comparison, the bottom 4 elements require 3 comparisons. Now, after we collect information in this binary tree, then we can write our average formula. When we take the average, we need to consider average of all these 7 cases. Average, 7 cases, yeah. And you need to factor in the number of comparisons for 3 different levels, right? Yeah, there are 3 different levels. The top level, only 1 comparison needed. And for the elements in the second level, 2 comparisons needed. And the elements at the bottom level, 3 comparisons needed. All right, yeah. Based on that, let us write the average number of comparisons for these 7 cases in this way. Yeah, this way, average. Okay, yeah. Because only 1 element in the top level. For 1 comparison, there is only 1 element. Right? For 2 comparisons, there are 2 elements. So 2 times 2. Total number of comparisons. Subtotal, yeah, that's the subtotal. So for top level, the subtotal number of comparisons, 1 times 1. For second level, the subtotal number of comparisons, 2 times 2. Okay, because there are 2 nodes, and each one requires 2 comparisons. So 2 times 2. For the bottom level, each one, the bottom one, yeah, so here, yeah, probably my arrow is wrong, all right? Yeah, I got confused, all right? Yeah, so for, oh, that's correct, right? Yeah, okay, yeah, my arrow is correct, okay, yeah. So the bottom one, each one requires 3 comparisons, but we have 4, okay? The number of nodes at the bottom level, there are 4. And each one, 3 comparisons. The subtotal, 3 times 4. All right? Then the total, you add up. These 3 subtotals, you add them up. That's the total. Then you divide it by 7. There are 7 cases. So the average number of comparisons 17 over 7. 17 over 7. Yeah. So if you write this mixed version, 2 and 3/7. 2 and 3/7. Yeah. Here you may argue this number is not very close to 3. Yeah. But when n is large, when n becomes larger and larger, the average larger and larger, then your average case is closer and closer to the worst case. Yeah. Okay. But the difference is less than 1. The worst case and the average case, the difference is always less than 1. So you can see how close they are. Less than 1 difference, how close they are when n is n, for any n number. Yeah. Yeah. That is the way we calculate the average case. Think about that. Okay? Yeah. Can you do this? Yeah. In this assignment, I didn't give you this question calculating average for the binary search. I didn't give you this kind of questions. Yeah. But later, sometime, yeah, I may need to give you this kind of questions. Yeah. So you need to understand this example. Okay? Yeah. And later, when I give you questions, I may not give you power of 2 minus 1. So here I give you power of 2 to the k minus 1. Yeah. Because this is the easiest case for you to do the calculation. Yeah. Later, I can give you, arbitrary positive integer number and ask you to do the calculation. Okay? Yeah. All right. Yeah. All right. Yeah. Then the last topic, B.4, introduction to the selection problem. Selection problem. Yeah. We learned some finding the minimum is a special case of the selection problem. But here we need to look at the general selection problem. Yeah. All right. So here, let me just give you some short introduction of the selection problem. Yeah. Problem number 12, the general selection problem. So what's that? Given an array and a positive integer k, how to find the kth smallest element? Kth smallest element for any given k number. Yeah. So here you can see the median is a special case of the selection problem, right? Finding the median, because you can select the k that corresponds to the middle position. How about that? Yeah. You can select the k, for example, you can select k equals the floor function of n over 2. How about that? When you select this k, you get a median. Yeah. Here, we also call kth order statistic. Yeah. So the formal name for this kth smallest element. Yeah. Kth order statistic. Yeah. All right. So here, another term, rank k. Yeah. We also use this rank term for this element. For example, the minimum element, the minimum of the array, that's the rank equals 1 for minimum. Okay, the rank equals to n for maximum. rank equal to n. Okay, rank equal to 1 minimum. Yeah, median. Yeah, so you can see that's the selection problem, the general selection problem. Yeah, the question: we need to solve this general selection problem. Okay, yeah, we need to use the fastest algorithm to solve the selection problem. Okay, yeah. And the data is unordered. If it's ordered, that's too easy, right? Yeah. If it's ordered, we just take that K and we can go to the right position to find the correct element immediately. That's simple. Too trivial. We do not need to do anything. But when the data is ordered, then it's challenging. It is very challenging. Yeah. The next question, should we sort the array first? Should we sort the array first? Yeah. So here, actually, if you sort the array, then you do too much work. You do not have to sort the array in order to find the kth smallest element. You do not need to. Or in other words, you can use fewer number of comparisons to find the kth smallest element, then you sort that array. Okay, yeah, yeah, but this is a long discussion and we do not have time today. Yeah, so I will do some further discussion on this topic next time. Yeah, yeah, and our part A of module 4, I have one last topic. That's an example. I didn't complete it. I will leave that one because that's just that is one example. I will leave that example in our review session. Yeah, because in our review session, I talk about examples, right? Yeah, talk about questions, examples. So I leave that part to our review session. Yeah, review part. Yeah. All right, so let me stop.